For most of Earth's history, life was small, soft, and simple. Then, in a window of geological time barely long enough to notice, almost every basic body plan in the animal kingdom appears in the rocks at once, including ours. Eyes. Legs. Guts with a mouth at one end and an exit at the other. Shells, claws, spines, brains. Almost all of it turns up in the same short interval, and almost none of it is there before. We call it the Cambrian explosion. It began roughly 538.8 million years ago, and it lasted somewhere between 13 and 25 million years. That sounds like an eternity. Set against the 4.5 billion years of Earth's history, it is a long weekend, and it produced the basic architecture of nearly every animal alive today. The strangest thing about the Cambrian explosion is that we knew about it before we knew about evolution. It was noticed as a problem, and specifically as Charles Darwin's problem. The first Cambrian fossils described were trilobites, written up in 1698 by Edward Leud, curator of the Oxford Museum. Nobody yet had a framework for what an ancient extinct animal even was. By the 1840s, William Buckland had noticed something odd in what were then called the primordial strata. Fossils seemed to arrive abruptly. Below a certain level in the rock, apparently nothing. Then, in 1859, Darwin published On the Origin of Species. His theory needed slow, gradual change, with ancestors below descendants in the rock. And below the Cambrian, he could not find the ancestors. He was blunt about it. He called this sudden appearance of trilobites, with no apparent antecedents, undoubtedly of the gravest nature, among the difficulties facing his theory. His answer was that the record must be incomplete, that earlier seas had swarmed with life whose fossils we simply had not found. In a later edition, he admitted, plainly, that he could give no satisfactory answer. For a while, some of the leading geologists took the rocks at face value. By 1859, Roderick Murchison was convinced that the lowest fossil-bearing layer showed the origin of life itself. Charles Lyell disagreed. It is worth pausing on how good a question this was. If complex animals really did appear from nothing, evolution as Darwin described it was in serious trouble. The stakes were not small. Charles Walcott, who we will meet properly in a moment, proposed a tidy solution, a missing interval of time he called the Lippalian, unrepresented in the rocks, during which the ancestors quietly evolved. He was wrong about the mechanism, but right about the instinct. There was an earlier world. It simply did not fossilize the way later worlds do, because almost nothing in it had hard parts. Since Darwin, that earlier evidence has turned up. Rocks at Warrawoona in Australia, claimed to be 3,850 million years old, have been said to contain fossil stromatolites, stubby pillars built by colonies of microorganisms. Fossils of more complex cells, eukaryotic cells, the kind that build animals, plants, and fungi, have been found in rocks around 1,400 million years old, in China and in Montana. And, in rocks dating from about 580 to 543 million years ago, sits the Ediacaran biota, organisms large enough to be multicellular, and very unlike anything alive today. The Ediacaran world is genuinely strange. Fronds, discs, quilted mattresses of tissue. Many of them have no mouth, no gut, no obvious front or back. Some may not be animals at all, in any sense we would accept. In 1948, Preston Cloud argued that a period of eruptive evolution had occurred in the early Cambrian. But even as late as the 1970s, nobody could see how the relatively modern-looking animals of the Middle Cambrian had arisen. Between the Ediacaran and the trilobites lies a group of fossils with an unglamorous name and enormous importance, the small shelly fauna. Mineralized, often only a few millimeters long, and almost continuous through the interval. The term was coined in 1975 by Samuel Matthews and Vladimir Misurzewski. One specialist has pointed out that it is a poor name because the fossils are not always small and commonly not shelly. Nobody has found a better one. Some are entire skeletons of small organisms, the mysterious Claudina, some snail-like mollusks. But most are fragments, pieces of sponges, mollusks, slug-like calcareids, brachiopods, echinoderms, disassembled and scattered. These matter because they record the moment life started building with minerals. And they raise the obvious question, after 3 billion years without skeletons, why start now? One early idea was chemical, a sudden rise in the ocean's calcium. But many of these fossils are made of other minerals, including silica, which weakens that explanation considerably. The likelier answer is grimmer. The first hard parts appeared about the same time as the first burrows dug to escape being eaten. Skeletons and hiding show up together, which looks a great deal like an arms race. Predation is the engine that makes an explosion plausible. Once something eats you, every improvement, armor, speed, burrowing eyes, pays for itself immediately. And every improvement forces a reply. There is a second possibility, less dramatic and probably also true, Mineralized skeletons are simply strong and cheap. They can take less energy to build than an all-organic one, and animals used whatever minerals were easiest to reach. Whatever started it, the result is a fossil record that changes character completely. Before, almost nothing preserves. After, the seafloor is littered with parts that survive burial, and we can finally see what is happening. But hard parts alone would still leave us blind to most of it. Something like 2/3 of the living animal phyla have never been found as fossils at all, because their bodies are soft and decay long before they can be buried. Which is why this entire story depends on a handful of freak locations, places where soft tissue was buried so fast that it left an imprint. Paleontologists call them Lagerstätten. The great Cambrian ones are the Mao-Shinshan shales of Zhejiang in Yunnan, China, Sirius Passet in Greenland, the Burgess Shale in British Columbia, and the later Orsten beds of Sweden. And in 2019, another one, the Xinjiang biota, on the Danshui River in Hubei province. More than 20,000 specimens, jellyfish, sea anemones, worms, sponges, arthropods, algae, dated to around 518 million years ago. In some of those specimens, the preservation is so fine that you can see muscles, gills, mouths, guts, and eyes. Around half the species found were, at the time of reporting, entirely new to science. The most famous of all of them was found by accident, at the end of a field season, high in the Canadian Rockies. Charles Doolittle Walcott was born in 1850 in New York State. His father died when he was 2. He left school at 18 without finishing, and that was the end of his formal education. He collected fossils commercially, then worked as an assistant to the state paleontologist of New York, lost the job after 2 years, and was recruited into the newly formed United States Geological Survey. From there, the rise is remarkable. Chief paleontologist by 1893, director of the Geological Survey the year after, and in 1907, secretary of the Smithsonian Institution, a post he held until his death. On the 30th of August 1909, near the end of the season's fieldwork above the town of Field in British Columbia, he found a band of dark shale with soft-bodied animals pressed into it. He returned in 1910 with his sons, his daughter, and his wife, and opened a quarry on the flank of Fossil Ridge. He came back nearly every year until 1924. By the time he stopped, aged 74, he had collected more than 65,000 specimens. He kept describing them until he died in 1927. And here the story takes its most human turn. Walcott, following the scientific opinion of his time, tried to fit every one of these animals into groups that already existed. A jellyfish, a sea cucumber, a shrimp. It is easy to be unkind about that from here, but it is what everyone did. The assumption that ancient animals must belong to modern categories was not a personal failing, it was the water everybody was swimming in. The consequence, though, was that the strangest fossil collection ever found sat in the drawers of the Smithsonian for decades, filed as curiosities, described as ordinary. In 1962, Alberto Simonetta went back to the specimens for a first-hand reinvestigation. It became clear that Walcott had barely scratched the surface, and that these organisms did not sit comfortably in modern groups at all. Then the Geological Survey of Canada reopened the quarry, at the urging of a trilobite specialist at Cambridge named Harry Blackmore Whittington. A second quarry was opened about 20 meters higher up the ridge. Whittington, with 2 research students, Derek Briggs and Simon Conway Morris, began working through the collection again, properly, with new techniques and fewer assumptions. What came out of that reassessment rewrote the whole picture. Many of the animals were bizarre, some bore only the slightest resemblance to anything alive, and the most famous of them was so odd that the audience laughed. Its name is Opabinia, after Opabin Pass, near where it was found. Walcott had collected 9 nearly complete specimens in 1911 and described them the following year. In 1975, Whittington published a detailed description based on painstaking dissection and photographs lit from many angles. It was that presentation that produced the laughter. Because Opabinia had 5 eyes, 2 near the front pointing up and forward, 2 larger on longer stalks at the rear pointing up and sideways, and a 5th between them pointing straight up, and a hollow, flexible proboscis, striated like a vacuum cleaner's hose, about 1/3 of the body's length, projecting down and forward from under the head, and ending in a grasping claw with 5 inward-pointing spines. Its mouth was underneath, behind the proboscis, and faced backwards, so its gut made a U-turn on its way to the tail. The snout reached food and passed it back into that reversed mouth. It was small, 4 to 7 centimeters head to tail. It lived on the seafloor, probing the sediment for soft food. Fewer than 20 good specimens have ever been described. At first, it was thought to belong to no known phylum at all. Studies since the late 1990s place it more comfortably, a basal arthropod related to Anomalocaris and its kin. Which brings us to the best detective story in paleontology. Anomalocaris was assembled, over a century, out of 3 separate animals that were not animals. In 1886, Richard McConnell of the Geological Survey of Canada climbed Mount Stephen in British Columbia and found abundant trilobites, along with 2 specimens nobody could identify. 5 years later, Henri Marcami collected 48 more of the same unknown things. In 1892, Joseph Frederick Whiteaves described all 50 of them. He decided they were the abdomens of shrimp-like crustaceans and gave them a name that quietly admits confusion, Anomalocaris from the Greek for anomalous and for shrimp. The unlike other shrimps, because that is what it looked like, a segmented, jointed thing ending in spines. In fact, it was not a body at all. It was the animal's grasping front appendage, and the animal was very much larger. Meanwhile, Walcott had found a strange ring-shaped fossil with a hole in the middle. He decided it was a jellyfish and named it Petoyat. It was, in fact, the creature's mouth. He also described a soft, lumpy fossil he named Lagania, which he took for a sea cucumber. That was the body. 3 names, 3 phyla, 3 separate mistakes, all of them the same animal. It took until the 1970s for Whittington's team to put it together, and even they went wrong on the way. In 1978, Conway Morris recognized that the mouthparts of 2 of those fossils were identical. What finally emerged was a swimming predator with flaps running down both sides of its body, huge compound eyes packed with lenses, and a pair of segmented grasping appendages at the front. Estimated at roughly 34 to 38 centimeters long, excluding those front appendages and its tail fan, it was one of the largest animals of the Cambrian, and among the earliest examples of an apex predator. Stephen Jay Gould called its story a tale of humor, error, struggle, frustration, and more error, culminating in an extraordinary resolution that brought pieces of 3 phyla together in a single reconstructed creature. And that is the real lesson of the Burgess Shale. Not that the Cambrian was full of monsters, that we spent 80 years looking at the pieces and could not see the animal because we already knew what animals looked like. In 1989, Gould published Wonderful Life and brought all of this to an enormous general audience. His argument was as much philosophical as paleontological. He suggested that Cambrian life was more disparate in body form than everything that has survived since, that many of these lineages were experiments which simply ended, and that the survivors were not obviously the best. It is a genuinely unsettling idea. Rerun the tape of life, Gould argued, and you would very likely get a different set of winners, and quite possibly no us at all. Both Whittington and Gould, differing on details, proposed that all modern animal phyla appeared almost simultaneously in a short span of geological time. That view fed directly into punctuated equilibrium. Punctuated equilibrium, developed by Niles Eldredge and Gould in the early 1970s, sees evolution as long intervals of near stasis, punctuated by short bursts of rapid change. The Cambrian is its showpiece. But Gould's interpretation leaned heavily on Simon Conway Morris's reanalysis of Walcott's work, and Conway Morris strongly disagreed with the conclusions Gould drew from it. His counter-argument was that almost all the Cambrian animals can, in fact, be classified into modern phyla, not alien experiments. Early, unfamiliar members of groups that are still here. The tool that dissolved much of the argument is the idea of a stem group, the extinct early relatives that branch off before a modern group's last common ancestor. They look wrong because they are early, not because they are alien. Opabinia is the perfect example. Once thought to belong to no known phylum, it is now understood as a basal arthropod, a cousin, not a stranger. The weirdness was real. The alienness was not. There is a second complication, and it is a beautiful piece of scientific self-awareness. It is called the Signor Lips effect, and it says, organisms almost always exist before they first appear in the fossil record. Because fossilization is rare, the first specimen you find is never the first individual that lived. Every origin in the rock record is therefore later than the true origin, sometimes by a great deal. Molecular clocks, estimating divergence times from accumulated DNA differences, offer another view, but they are fallible. Different techniques produce estimates that vary by a factor of 2. What recent clocks do suggest, combined with the constraints of the fossils, is a sustained period of diversification running through the Ediacaran and into the Cambrian, not a starting gun, a long build. So, was there an explosion at all? Yes, but the word does a lot of damage. What the rocks show is a real fast diversification, sitting on top of a much longer and quieter history that fossilizes badly. Consider the animal that dominates the story's beginning, the trilobite. They first appear in the fossil record around 521 million years ago, and they were already diverse and worldwide shortly afterwards. They had a mineralized exoskeleton of calcite, which fossilizes beautifully, which is exactly why they dominated the early picture, and why Darwin's problem looked the way it did. Over 22,000 species have been described. They lived in the oceans for almost 270 million years, vastly longer than the dinosaurs and longer than mammals have existed. They crawled, swam, scavenged, filtered, hunted. Some may have lived in partnership with sulfur-eating bacteria. The largest were more than 70 centimeters long and may have weighed 4.5 kilograms. Their diversity fell hard through the mid to late Devonian in a series of extinction events. They limped on, in low numbers, for another 100 million years. The last of them disappeared in the end, Permian extinction, about 252 million years ago, which is worth holding on to. The animals that made the Cambrian look like an explosion are also, mostly, gone. What survived is not the impressive part. What survived is the interesting part. Because, among all those bodies, in the same rocks is something unremarkable, the earliest chordates. Small, soft, easily missed. The lineage with a stiffening rod down its back. That rod becomes a spine. That lineage becomes fish, then amphibians, then everything with a backbone, including the animal watching this. We are a Cambrian body plan that got lucky. And this is where a story about half-billion-year-old rocks becomes personal. Your body plan, bilateral, segmented, one mouth, one gut, a nerve cord, paired eyes, was settled then and has never been renegotiated since. Evolution has redecorated endlessly. It has not rebuilt. Every vertebrate since is a variation on a scheme that was locked in while trilobites were still new. There is a coda about the Burgess Shale that says something about how science actually works. Collecting there became politically difficult from the mid-1970s as its significance was recognized. It was made a World Heritage Site in 1980 and folded into the Canadian Rocky Mountain Parks designation in 1984. In 2022, it was named among 100 geological heritage sites worldwide. And it keeps producing. Desmond Collins of the Royal Ontario Museum identified further outcrops. In 2012, another was announced in Kootenay National Park. 15 days of collecting there in 2013 turned up 50 animal species. Those sites, in the phrase used of them, continue to yield new organisms faster than they can be studied. The Cambrian is not a solved problem. It is an open excavation. So here is where it leaves us. Darwin's difficulty was real, and he was right to be troubled by it. The ancestors he wanted did exist. They were soft, small, and almost unfossilizable, and we needed a century and a half to find their traces. The explosion was real too. A genuine, rapid diversification, most likely driven by predation and the arms race it started, once something in that dark water learned to eat something else. And it happened in the dark, in silt, in seas with no fish and no sound, among animals that looked like nothing you have ever seen, and it decided, permanently, what an animal is. 65,000 specimens sat in a museum drawer for 50 years before anyone realized what they were looking at, which raises a question worth carrying out of here: what else is already collected, already cataloged, and still not understood?